Hello everyone, and welcome to the video covering the different operations we can do with complex numbers. When we're working on these are going to be complex numbers that are in the polar form that we just covered in the previous classes. The skill objectives for this particular video are: number 1, to find the product of two complex numbers; number 2, find the quotient of two complex numbers; number 3, raise a complex number to an integer power; number 4, find the nth root of a complex number; and finally, number 5, solve polynomial equations. The conceptual objectives are: 1, to go through at least understand the derivation for the identities that we're going to use to find the product and quotients of complex numbers, and to relate DeMoivre's theorem for complex numbers to the product rule for complex numbers. DeMoivre's theorem is one way that we have to quickly go and deal with the powers, finding powers of a particular complex number. The thing to remember on this, though, in each case, there are going to be times when you'll be given complex numbers in rectangular form. In order to do all of these, you're going to have to put those complex numbers into that polar form that we've been dealing with. Now, the first thing we want to do is go through the derivation of the product, how we find the product of two complex numbers that are written in polar form. So in this case, what we're going to do is we want to show that the product of two complex numbers, z1 and z2, is equal to this expression right here. So in this problem, we're going to let z1 equal r1 times the cosine of theta 1 plus I sine of theta 1. And z2 is r2 times the cosine of theta 2 plus I sine of theta 2. Therefore, the product of those two is going to be r1 times r2 times the cosine of theta 1 plus I sine of theta 1 times the cosine of theta 2 plus I sine of theta 2. All we did there is just go through and take the two magnitudes, multiply them together, and then we have the two expressions in the parentheses still there. At this point, what we need to do is FOIL this out. So I'm going to go through, take cosine of theta 1 times cosine of theta 2 and I sine of theta 2, and do the same thing with I sine of theta 1, distribute it inside. And when I do that, I'm going to get this expression right here. Now remember on this that the I squared right here is equal to -1. And because of that, and when I start moving things around, I'm going to get that this expression, this whole expression right here, can be thought of as r1 times r2 times cosine theta 1 times the cosine of theta 2 minus, from over here, sine of theta 1 sine of theta 2 plus the i's. I pulled out the common factor of i's on the other two. I times the cosine of theta 1 sine of theta 2 plus sine of theta 1 cosine of theta 2. Now, thinking back to what we did in chapter 6, I know it's back again, but what we did before is that these two expressions right here happen to be the same expressions as the cosine sum and sine sum formulas from what we did back in chapter 6. So this whole expression right here just becomes the r1 times r2 times the cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Take a minute, make sure you're comfortable with this algebra that we did. If you're not, make sure to mark it and come back and make sure to ask about it in class. Now that we have that formula, the identity that we can use for the product of two complex numbers, let's actually do a problem. This first one is going to be where the complex numbers are written using degree measures. So on this particular problem, z1 is equal to 3 times the cosine of 130 degrees plus I sine of 130 degrees. And z2 is 4 times the cosine of 170 degrees plus I sine of 170. So remembering this particular identity right here, that z1 times z2 is the product of the magnitudes times the cosine of the sum of the arguments plus I sine the sum of the arguments. So for this particular problem, z1 times z2, I know is going to be 3 times 4 times the cosine of 130 degrees plus 170 degrees plus I sine 130 degrees plus 170 degrees. 130 plus 170 happens to be 300, so that's going to be 3 times 4 is 12. 12 times the cosine of 300 degrees plus I sine of 300 degrees. Now, at this point, at this particular point, we might want to go and they may ask you to go through and give the answer in rectangular form. And so in this case, we know for 300 degrees that the cosine of 300 degrees is equal to 1/2. And the sine of 300 degrees, I have a mistake there, is going to end up being negative square root 3 over 2. And so, on this problem, this becomes 12 times 1/2 plus I times a negative square root 3 over 2 equals 6. When I distribute the 12 in there, I get 6, and that would actually end up being, I have plus a negative, but it'll be 6 minus 6I times the square root of 3. That would be the rectangular form of that complex number. What I'd like you to do is pause the video, and I'd like you to go find the product of the two complex numbers we have here and here. Find that product and express that product in rectangular form. So go ahead, pause the video. Once you have that set, come back and we'll talk about what you need to do. Welcome back. So in this particular problem, I want to go through and find z1 times z2. So when I'm working on this one, z1 times z2, it's going to be square root of 7 times the square root of 3. So z1 times z2 will be square root of 7 times square root of 3 is square root of 21 times the cosine of the sum of the arguments. So it's going to be the cosine of 5 pi over 15, which will be pi over 3, plus I sine pi over 3. And if I want that in rectangular form, it'd be the square root of 21 times 1/2 plus I square root of 3 over 2. Or I could multiply it out. I'd have square root of 21 over 2 plus I times the square root of 21 times 3 is 63 over 2. And I could simplify it if I want, but that would be fine as well. So hopefully that's what you came up with. If that isn't, check your calculations, see if you can discover where the mistake happened. If not, be sure to ask about it in class. Now that we have the product down, let's take a look at how we go through and find the quotient of two complex numbers. So in this case, again, we'll have z1 is r1 cosine theta 1 plus I sine of theta 1, and z2 is r2 cosine theta 2 plus I sine of theta 2. Now the thing, we're not going to actually go through the complete derivation of it. If you want to see that, it is on page 730 of your textbook. But what I want you to do is think about it this way. We know that the product of two complex numbers is equal to this. Okay? So I want you to think about what you think the quotient is equal to. But keep in mind that the quotient is the opposite operation. Okay? So take a minute, think about what you think that quotient would be equal to in an expression similar in this form, and then come back and we'll talk about what it actually comes out to be, see how close you were. Welcome back. So in this case, what we're going to look at is we want to go through and see what you can see, compare what the, figure out what the quotient of two complex numbers is. Now keep in mind on this one, we're dividing these. And what you would end up doing, if you take a look at the derivation in the book, you're going to notice that they're going to multiply by the conjugate of this denominator, which you should be familiar with. But the end result is this. Since these are opposite operations, what you have is that when I take the quotient of Z1 over Z2, this is going to be R1 over R2 times the cosine, and again, remembering these are opposite operations, cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. That's what you should end up with. Take a look here and notice how we have the opposite operations are coming into play. Number one, with the product, it was a product there. With the quotient, we're using a quotient of the magnitudes. When we had the product, it was a sum. We added the two here. And given that division is the opposite operation, it makes sense that we would have the opposite operation in terms of the arguments as well. We'd have the difference of the arguments. Okay. Make sure you're comfortable with that. Then let's take a look at a couple examples. The first example we want to look at is where Z1 is equal to 8 times the cosine of 5 pi over 8 plus I sine 5 pi over 8. And Z2 is 4 times the cosine of 3 pi over 8 plus I sine of 3 pi over 8. Now remembering this, that the quotient of two complex numbers is going to be the quotient of their magnitudes times the cosine of the difference of their arguments plus I sine of the difference of their arguments. So in this case, for these two complex numbers we have, it's going to be 8 over 4 times the cosine of 5 pi over 8 minus 3 pi over 8 plus I sine 5 pi over 8 minus 3 pi over 8. Now 5 pi over 8 minus 3 pi over 8 is 2 pi over 8, which reduces to pi over 4. So 8 over 4 is 2 times the cosine of pi over 4 plus I sine of pi over 4. In this case, if I want the rectangular form, the cosine and sine of pi over 4 are both square root of 2 over 2. So I have 2 times the square root of 2 over 2 plus I times the square root of 2 over 2. When I distribute the 2 inside here, I'll get square root of 2 plus I square root of 2. So there is the rectangular form of the quotient of those two complex numbers. What I'd like you to do, I'd like you to pause the video, and I'd like you to go and find, for this particular problem, where Z1 is 10 times the cosine of 82 plus I sine of 82. These are degrees. And Z2 is 20 times the cosine of 22 degrees plus I sine of 22 degrees. I would like you to go and find the quotient. So pause the video, find that quotient. Once you do, come back. We'll take a look and see how you did. Welcome back. So on this particular problem, what you should have come up with is that Z1 over Z2 would come out to be 1/4 plus I times the square root of 3 over 4. When you do this problem here, when you actually set it up using the quotient rule that we have up here, that would be equal to, it would be equal to 10 over 20 times the cosine of 82 degrees minus 22 degrees plus I sine of 82 degrees minus 22 degrees, which comes out to equal 1/2 times the cosine of 60 degrees plus I sine of 60 degrees. And when you go through and put it in rectangular form, that would come out to be that. So take a look at your calculations, double check. If you did not get this, double check your calculations and see if you can identify what mistake you made. If not, mark it and again, ask about it in class. Now let's take a look at what happens, see if we can identify a pattern and see a pattern that happens when we go through and find the powers of different complex numbers, of a complex number. So in this case, notice we're not going to have the subscript now because we're just going to let z, in this case, equal r times cosine of theta plus I sine of theta. I'm not dealing with two different complex numbers. I'm just going to take powers of this one, so I don't need the subscript. So what happens on this one, and we want to keep in mind how we find the product of two complex numbers. In this case, z squared is going to be this z times itself. So I'm going to get r times the cosine of theta plus I sine of theta times the cosine of theta plus I sine of theta, which when we do that, what we saw in the previous, we dealt with the product, this is just going to end up being where we're going to have the product of these two, which is r squared, times the cosine of the sum of the two arguments plus I sine the sum of the two arguments. So in this case, that becomes r squared times the cosine of 2 theta plus I sine of 2 theta. That would end up being the value of r squared, the square of this particular complex number. Now, when we deal with the cube of the complex number, that is going to be z squared times z. Well, we know that when we multiply two complex numbers, it's going to be the product of their magnitudes. So the magnitude of z squared is r squared. The magnitude of z is r, times the cosine and sine, well, cosine of the sum of their arguments. So I have 2 theta plus I sine of 2 theta plus theta. And when I combine that, that equals r cubed times the cosine of 3 theta plus I sine of 3 theta. Then we go to z to the 4th. Raise the complex number to the 4th power. Again, that's equal to z cubed times z. And so when I multiply those, it'll be r cubed times r times the cosine of 3 theta plus I sine of 3 theta plus theta. So I get r to the 4th times the cosine of 4 theta plus I sine of 4 theta. Now at this point, I think you should be noticing a pattern. I'm taking, when you look at all of these three that we've done so far, you'll notice that the power that I'm taking on the complex number, when it's written out in its polar form, when I take that power, on terms of the magnitude is raised to the same power. But the other thing you have is that the argument of the original angle is multiplied by that power. So in general, what we have is z to the n equals r to the n times the cosine of n times theta plus I sine of n theta. This right here will formalize in a bit. So what we have now is what's called DeMoivre's theorem. And DeMoivre's theorem is this: if z is equal to the complex number r times cosine of theta plus I sine of theta, then z to the n is equal to r to the n cosine of n times theta plus I sine of n theta. Where, when n is a positive integer, where basically n is greater than or equal to 1. Here's an example. We're going to let z equal 3 times the cosine of pi over 3 plus I sine of pi over 3. So let's take this complex number, raise it to the 4th power, and then we'll express it in its rectangular form. So by DeMoivre's theorem, which is what we have up here, z to the 4th is going to be 3 to the 4th times the cosine of 4 times pi over 3 plus I sine of 4 times pi over 3. Well, in this case, 3 to the 4th is 81, and that'll be the cosine of 4 pi over 3 plus I sine of 4 pi over 3. So cosine of 4 pi over 3 is negative 1/2. Sine of 4 pi over 3 is negative square root 3 over 2. So in this case, this problem is equal to 81 times the quantity of negative 1/2 minus I squared root of 3 over 2. If I distribute the 81 inside, I'll get negative 81 over 2 minus 81I squared root of 3 over 2. Again, pause the video right now. Make sure you're comfortable with the calculations that I have. Make sure that you have them written down. And if you have any questions, if you're not sure about something, again, make sure to note it so you can ask in class. Now here's another example that we'll have. What they're going to ask you to do is we're going to be asked to go and find, we're going to take a complex number that's written in rectangular form to a power. Okay, so one of the things you're going to want to do, the first thing you're going to want to do on this is to remember to go through and plot this in the complex plane. So if you remember on this, in terms of the when you deal with the complex name, the plane, the x-axis is the real portion, the real axis. The y-axis is the imaginary axis. And so my real portion here is square root of 3. My imaginary portion is negative 1. And so I go to square root 3 and negative 1. It gives me this point. So when I plot this complex number, we're in quadrant 4. Now that's going to be helpful for us in terms of identifying that the argument. So the next thing I want to do is write this in its polar form. Well, the magnitude is the square root of the square root of 3 squared plus negative 1 squared, which ultimately just becomes the square root of 4, which equals 2. The argument is that theta is going to be equal to the inverse tangent of negative 1 over the square root of 3. Well, the inverse tangent of that comes out to be negative pi over 6. Okay, so in this case, our complex number z is equal to 2 times the cosine of pi over 6 minus I sine of pi over 6. Because remember here, the cosine of a negative cosine's an even function, so the negative sign just drops off. Sine is an odd, so when we have a negative there, it moves on the outside. Okay. Now, what we want to do, we want to take this right here, raise it to the 8th power. Well, I know once we have it in this form, I know that in this case to the 8th power, I'm going to take my magnitude, raise it to the 8th power, times the cosine of 8 times the pi over 6, minus, in this case, I sine of 8 times pi over 6, which simplifies 2 to the 8th is 256 times the cosine of 4 pi over 3 minus I sine of 4 pi over 3. And now this is the polar form of that solution. If I want the rectangular form, the cosine of 4 pi over 3 is negative 1/2. The sine of 4 pi over 3 is a negative square root 3 over 2, but that's a negative there, so that will make that a positive. So it'll be negative 1/2 plus I squared root of 3 over 2. Distribute the 256 inside. 256 times the negative 1/2 is negative 128, plus the 256 times I squared root of 3 over 2 is 128 I squared root of 3. So this would be the 8th power of, this would be square root of 3 minus I to the 8th power would come out equal to that. Again, pause the video, make sure you're comfortable with the calculations I have here, especially how we went from here to here. If you're not, make sure to ask it in class. And once you're ready, come back, restart, and we'll move forward. All right. Now let's look at the roots of a complex number. Now in this case, what you have to remember here is you have to remember what it means for two complex numbers to be equal. If they are equal, they will have the same magnitude. That's a guarantee, okay? But if two complex numbers are equal, it doesn't necessarily follow that their arguments have to be the same. And the reason is because the argument is, in these cases, the argument is theta. And so a measure of theta or any angle coterminal to theta would also give the same complex number. So you have to keep that in mind. So in this case, the arguments, in order for two complex numbers to be equal, their arguments must be the same, but their magnitudes must be the same. Their arguments have to be coterminal to each other. So in this case, we're going to go through and define our two complex numbers. One is z. Z is equal to r times the cosine of theta plus I sine of theta. Another complex number we have is w. W is equal to s times the cosine of alpha plus I sine of alpha. Now, because we're working on identifying the roots of a complex number here, we're going to go through and put one other relationship, and that is that w is guaranteed. W is the nth root of z. So therefore, w equals z to the n, or that nth root of z. And therefore, z is equal to w to the n power. So if I take this and solve it for z, I'm going to get this. And now I have that z equals w to a power. So, by DeMoivre's theorem, w to the n is equal to its magnitude raised to the n power times the cosine of n times its argument plus I sine of n times its argument. So I get that w to the n is s to the n times the cosine of n times alpha plus I sine of n times alpha. So, therefore, we know this here is equal to z, and z is this. So I have z, that r cosine of theta plus I sine of theta is equal to s to the n times the cosine of n times alpha plus I sine of n times alpha. Now again, remember, in order for complex numbers in polar form to be equal, we know their magnitudes have to be equal. So therefore, I know s to the n has to equal r. And therefore, if I solve it for s, s is r to the 1 over n power. The other thing, I know that their arguments have to be coterminal angles. So therefore, I know that n times alpha, whatever n times alpha is, it's going to be theta plus 2k pi. Now remember, we're working in radians, and 2k pi, where k is an integer, just means I'm adding one full revolution. I'm creating the different angles that are coterminal to theta. So in this case, I know n times alpha is equal to this for some value of k. I don't have to actually find out which one it is, but I know it is true for some value of k. And then when I solve this for alpha, I get alpha equals theta plus 2k pi over n. And so when we go back to w, remember w is the nth root of z. I can replace s with r to the 1 over n, because that's what it's equal to, and I'm going to replace the alpha with theta plus 2k pi over n. And therefore, since z to the 1 over n equals w, I know the nth root of z is going to be r to the 1 over n plus the cosine of theta plus 2k pi over n plus I sine of theta plus 2k pi over n. Again, pause the video. There's a lot of stuff happening here. Make sure you're comfortable with it. Once you are, come back. We'll move forward. If you're not, be sure to mark it and talk and ask about it in class next time. Now, let's take a look at going through and finding the roots. In this case, what I want to do is I want to find the cube roots of z equals the square root of 3 minus I. Now, we've dealt with square root of 3 minus I. Earlier, we had, if you want to look back in your notes, you might recall that in this case, square root of 3 minus I was equal to, in polar form, 2 times the cosine of pi over 6 minus I sine of pi over 6. So that's how I'm going to write this. Now, I also know that the nth root of a complex number is r to the 1 over n times the cosine of theta plus 2k pi over n plus I sine of theta plus 2k pi over n. Remember, if you're working in degrees, this would end up being 360 times k, but we're working in radians right now. So I know the cube root of z, our z value of this number, of this square root of 3 minus I, which is equal to this, is going to be 2 to the 1/3 times the cosine of pi over 6 plus 2k pi, that whole thing over 3, minus I sine of pi over 6 plus 2k pi, that whole thing over 3 as well. Now, this is a little bit messy. So what I want to do is I want to simplify this, okay? And I want to simplify it so I can kind of work with it. So what you have here, in this part right here in the green, is the simplification of that expression, pi over 6 plus 2k pi over 3. That is, this thing, dividing by 3 is the same as multiplying by 1/3. When I distribute the 1/3 inside, I will get pi over 18 plus 2k pi over 3. But remember on this, I need to go and get a common denominator. So in this case, my common denominator is 18, so I'm going to multiply top and bottom times 6, and when I do that, that will end up giving me pi over 18 plus 12k pi over 18, which when I combine that, I now have a common denominator. I can put it into a single fraction. And the only thing I'm going to do now is I'm going to pull out that factor of pi. Okay? I'm going to pull out that factor of pi, so when I factor that out, I have pi times 1 plus 12k over 18. So I know this weird looking thing, yeah, it may not look, you may not feel like it looks much better, but it's a lot easier to work with in this form. So now what I know is that my cube root of z is equal to 2 to the 1/3 power, the cube root of 2, times the cosine of pi times the quantity 1 plus 12k over 18 plus I sine of pi times 1 plus 12k over 18. So now what we're going to do is we want to generate every solution. And here's something that's really cool. No matter what n is, in this case we have n equals 3. Because n equals 3, k is going to have, in this case, 3 values. We're going to use k is going to have 3 values, and it always starts at 0. So k is going to start at 0, 1, and then the third one will be at 2. You'll always stop at 1 less than whatever n is. So if n was equal to 7, if I wanted the 7th roots, I'd use my expression, but I would go through and the k values would go from 0 to 6. The expression would be slightly different because instead of dividing by 3 up here, it'd be 7, but you get the idea. The values for k, the number n is going to tell you how many values that you're going to use for k, and you're always going to start with 0 and go to whatever one number less than n is. So in this case, I'm going to let k equal 0. When I put 0 in for k, I put 0 there, I get that the cube root is 2 to the 1/3, the cube root of 2, times the cosine of pi over 18 plus I sine of pi over 18. When I put 1 in for k, when k equals 1, now that'll be 1 plus 12, so I get the cube root of 2 times the cosine of 13 pi over 18 plus I sine of 13 pi over 18. And the last one, I'll put 2 in for k, and when I do that, 2 times 12 is 24 plus 1 gives me 25. So I get 2 to the 1/3 power times the cosine of 25 pi over 18 plus I sine of 25 pi over 18. In this case, those are not numbers that are going to be nice to work with. So we may ask you, if we ask you to go through and give the rectangular form, obviously you wouldn't be able to get the exact value. You'd have to go through and round it. I would round it probably to about 2 decimal places and just give it to me in 2 decimal places in its rectangular form. If I don't specify the rectangular form, just go ahead and leave it right like that. Okay. Now, as before, double check, look at my calculations, make sure again that you're comfortable with this simplification here, this in terms of that expression, and then how we went through and how we went and used this to get these 3. If you're not, make sure you mark it, ask in class. Otherwise, we got one more example to look at. Now, in this problem that we're going to look at, in this example, we want to go through and solve x to the 5th minus 1 equals 0. So therefore, I know x to the 5th is equal to 1. The one thing I'm going to want to do is I need to write that 1 in its complex form. Now you need to also remember on there that that 1 is 1 plus 0i. So in its complex form, this is equal to, 1 is equal to the cosine of 0 plus I sine of 0. Okay. Double check that if you don't remember that, but take a look. You'll notice cosine of 0 is 1, sine of 0 is 0, so we get to there. So now what this problem has been changed to is that x to the 5th is equal to the x to the 5th equals cosine of 0 plus I sine of 0. So I know x is equal to the cosine of 0 plus I sine of 0 to the 1/5 power. Okay. Now, the argument or the magnitude on this is 1, so I don't have to worry anything about that. So I'm going to take 1 to the 1/5 is 1. So in this case, using the root of a complex number identity that we had before, in this case, x is going to be equal to the magnitude of 1, if you will, times the cosine of 0 plus 2k pi over 5 plus I sine of 0 plus 2k pi over 5. If you simplify that, nice and easy, x equals cosine of 2k pi over 5 plus I sine of 2k pi over 5. Now, what we want to do, in this case, we know we have, because it's a 5th degree polynomial, there are 5 solutions. I want to find all 5. N is 5. So in this case, I'm going to use values for k. K is going to be 0, 1, 2, 3, and 4. If k is 0, we get that, which is what we had up here. And that makes sense because we know that one of the values here would be that 1 to the 5th is equal to 1. So there's one of them. When k equals 1, I put 1 in for k, I'll get cosine of 2 pi over 5 plus I sine of 2 pi over 5. When k is 2, I will get cosine of 4 pi over 5 plus I sine of 4 pi over 5. I'll put in 3 and 4, and I will generate each one of these. So these 5 values, those 5 numbers, would be the complex solutions to x to the 5th minus 1. Okay. Again, pause the video, make sure you're comfortable with that, and if not, make sure to mark it, ask about it in class. Otherwise, I hope you're feeling okay with this, and we will see you in our next class.